Hi, I'm Zach with HKN. Today we're gonna remake a video that we have on our channel already. Clancy made a while ago before we had this really sweet lightboard technology. So we're gonna redo it for visual effect mainly. It's about an RLC circuit. So this is there's gonna be a second order differential equation that describes the behavior of this circuit, and we're worried mainly about what the general characteristics of its transient response is. Maybe see we have symbolic values for our elements, so we're going to solve it using those values and see what types of values for these elements will give different responses. Mainly we're worried about what the damping looks like. It could be over damped, underdamped, or critically damped. So we're going to see what values of R, L, and C will result in that. So see, the way we start this, we should set up our differential equation. So we can do it like we would normally do a circuit. Let's see. Let's call this node right here V naught. And let's do KCL at this node. We'll sum the currents leaving the node, set it equal to 0, current there, and a current there. So we'll say that this current is equal to V naught minus our source V over R. We'll say that. Plus the current through this capacitor. Now, what's the current through a capacitor? We have this little thing here. This holds for any capacitor. If there's a voltage across it, the current through it is equal to the capacitance times the time derivative of the voltage. So the voltage across this capacitor here, we have this node set to ground, so the voltage is V naught. So the current through it is going to be C times the derivative of V naught, time derivative, plus we'll call this IL for now, because, okay, so we'll just set this equal to 0. And now we have two different variables in our equation. We don't really want that. We have current across the capacitor and the current through the inductor. Now, these things are in parallel, so they share a common current. And we can see that V naught is also, did I say they share a common current? Yeah. Okay, no, they don't share a common current. They share a common voltage because they're in parallel. And V naught is also the voltage across the inductor. So we could, every place we see V naught, we could set it equal to L di dt. So let's do that. Actually, let's rearrange this just a bit. We're going to move this constant V from our source over to this side of the equation. That will result in, I'm going to reorder the terms a little bit too. And I multiplied by R as well, right? So oh, that's wrong. Equals V. All right, so I moved our constant term over this side and multiplied through by R. Now, every time we see V naught, we'll set it equal to L di dt. That'll result in, so here we have the derivative of V naught, so we're going to have to take the derivative of that, right? So we'll have Rlc times the second derivative of V naught plus, let's see here, plus L di dt. I'm sorry. This should also be I plus R I is equal to V. Okay, so now our equation is all in terms of one variable. That variable is the current through the inductor. So we could have also manipulated this in such a way that we could use the voltage across these two things as our variable instead. That may be a little more intuitive, because probably what we'd be doing with the circuit is reading the voltage here. But that's not a big deal. The behavior of this current is going to mimic the behavior of this voltage. So either one will tell us about how this behaves. All right, so let's arrange these constants so that our second derivative term is by itself. So we'll go you know what, these orange markers are not good. So we're dividing through by Rlc. So L's will cancel there. We'll get 1 over Rc. And the R's will cancel here. We'll get 1 over Lc times I. We'll set that equal to V over Rlc. Right, okay, so there's our differential equation in the form we like to work with. And so from differential equations, we know that the solution to this is going to be the sum of our homogeneous solution and a particular solution, where a particular solution is any one value you can plug in for I. Say that makes, I'm sorry, any one value you could plug in for, I. That would make this thing equal, you know. So let's think about that for a second. What if we made I equal to a constant value of V over R? Any derivative of I would be 0 because it's constant, and we'd have V over RLC equals V over RLC. So that would be our particular solution, but we're more worried about the behavior of the transient response, and we can get that from our homogeneous solution. That means we set this side of the equation equal to 0. So let's do that in the next step we take here. A really good way to do this, and actually the way we kind of have to, I think, is to use Laplace transforms. So we'll set this equal to 0 and take the Laplace transform of this side. Now, when we do Laplace transforms of derivatives, anytime we see a second derivative, we put in s squared, first derivative, s, and then I itself can be thought of as the 0th derivative. So this is how we'd set up the Laplace representation of this. We would have I of s all times s squared plus, we keep the constant terms, so we know from probably from your differential equations class that the roots of this polynomial here will be in our response, our time response, in the form, so we know our time response will have, say we have two roots, R1, R2, two roots of this polynomial. Our response, I of t, will have the form some arbitrary constant that we're not worried about times e to the r1t plus another arbitrary constant times e to the r2t, where r1 and r2 are our roots. So that's why we're interested in finding the roots of this. How do we find the roots of that? We use that thing you probably learned in high school that you said you'd never use in your life called the quadratic equation. And we'll set that up in a minute here. All right, so what does the quadratic equation say? It says that minus b, well, okay. The solution to a quadratic formula, or yeah, quadratic equation. Sorry, this is a quadratic formula. It's equal to b squared minus 4ac over 2a, where those a, b, and c are all constants. So in our case, a, the first coefficient here is 1. B is 1 over RC, and C is 1 over LC. All right. So let's rewrite this a bit. This would lead to, in our case, 1 over. So I'm going to skip a couple steps, but you can verify them. We're going to kind of move this 2 up into the equation and sub everything in at the same time. All right, so now we have our quadratic formula set up with our symbolic values for R, L, and C. So now, depending on their values, the answer to this will take on a couple different forms. Let's say that's equal to S. Those are the values of S that satisfy this equation. So let's rename. So let's set these terms. Let's just rename them for the sake of convenience. Let's call 1 over 2 RC. Let's call it alpha. And let's call, this is really just manipulation so stuff works out for us. But let's call 1 over the square root of LC, well, we'll call it omega naught. Okay, so now that we've renamed these terms a little bit, we can rewrite this quadratic formula to say that S is equal to negative alpha plus minus root alpha squared minus omega naught squared. Is that right? Yeah. Yeah, okay, so now we have our quadratic formula in a pretty simple form, and we can look at its behavior. So let's go through, there's 3 different cases we can have here. First, let's work with the case where alpha is greater than omega. So if alpha is greater than omega, there'll be some positive term in this square root, and we'll get just some 2 real roots. We call this the overdamped case. So our response, we'll have 2 roots. We'll have and we don't know what the value of the roots are going to be because we're working symbolically, but we'll call them R1 and R2. And like we said before, our behavior of IT will be this. Chances are, okay, so we see we have a negative alpha here, and alpha is equal to 2RC, which none of these numbers can be negative, so negative alpha is always going to be negative. So chances are we'll get R1 and R2 will be negative. That's fine. That's actually better because that means these terms will die out over time and our transient response will approach our particular solution. Okay, so let's work with the next case where alpha is equal to omega. I think we call this critically damped. Okay, so what do we get here? This term inside the square root is equal to 0. And then we have just a repeated root at negative alpha. So so we learned in differential equations that when we have a repeated root, our solution has the form arbitrary constant plus another arbitrary constant times t times e to, I guess, since we're calling our roots negative alpha t. So that is what our response will look like for the critically damped case. I think this is what you'd usually aim for in a case where you're trying to smooth out a circuit's behavior to a step response. Okay, so let's deal with the final case where alpha is less than, alpha is less than omega. We call this overdamped. Okay, so when alpha is less than omega, this term inside this square root is negative, and we say, oh no, we can't take the square root of a negative number, but we can, and it results in an imaginary term here. And I don't know, someone somewhere decided to call this imaginary. I don't like that name. They're not really imaginary. They just always occur in like conjugate pairs and they cancel each other out. But anyways, we'll see what happens. So our roots will have the form. Let's call it, we'll have a root at r plus j beta. We don't, we don't know the exact values of these, but these are the types of numbers you're going to get, and we'll have on it r minus j beta. So the same principle holds. We really get the same solution as this, but we'll rearrange it to see what it means. So we'll have that I of t is equal to arbitrary constant times e plus another arbitrary constant times e to the other root, so r minus j beta. Okay, now we have a property of exponentials where if we multiply two exponentials together, we can make it into a single exponential with in sum their exponents, right? So the reverse is true. We can factor out e to the r out of both of these terms. We could get this into some form that is e to the rt times some other arbitrary constant, all multiplied by e to the j beta t plus e to the negative j beta t. And what is this? I don't know if you've had a class that you've gone over Euler's identities in yet, but this is equal to 1/2 cosine of beta t, this term right here. So ultimately this equals c times e to the rt times cosine of beta t. So we see that we'll have some oscillation in our response, and that's really exactly what, did I say overdamped? Oh my God. Sorry. This is overdamped. This is underdamped. So yeah, that's what underdamped means. We'll have some oscillation in our response to a step or an impulse. All right, that's that. Thanks.